Back with some more electrodynamics. And we saw earlier that we can go ahead and take a regular volume or area integral with the Jacobian. It's just that we have to put everything in the same terms. So when we integrate the bounds or the axis, we also take into account the variables of whatever it is, the vector field is or whatever, but the same type of integral. So it's the same type of integral with something multiplied with it. So I believe I left off on B. We just have C left. We'll go to the next homework, chapter 3. I know my integral is slightly off, but if I did make H equal A for this one, it'd be 2 pi A squared minus A squared plus A squared, 2A squared, negative 1 B 2 pi A over A squared minus 2 over square root of 2 over A. We have an incorrect integral, but about the gist of that one. I'll move on. So let me go to the problem and get the charge configuration. Here's an example 1. Example 1 looks like this. I do remember this one vaguely. We have charges any sort of hexagonal configuration. It's A in length. X, we have Y, and this is 1, this is 4. We want to find the electric field along the y-axis. So We know that by default, E equals K Q over R squared, and F equals EQ. Um, in this case, if I take, let's say, E1, that equals K Q1 over R squared. But R squared changes, so R squared is whatever that is. So this is Y. So A squared plus Y squared equals R squared. So E1 equals KQ over A squared plus Y squared. And the Y component cancels. The S component cancels with the one on the opposite side. So actually this is 6. So E6 Y equals E3 Y. E1 Y equals E2 Y, and E4 Y equals E5 Y. So we can say 2 E6 Y equals KQ over A squared plus Y squared, and the Y aspect be, if this is theta or sine theta, opposite, R equals square root of A squared plus Y squared. So 2 EBY equals KQ over A squared plus Y squared, uh, A squared plus Y squared 1/2. So that equals KQ A squared plus Y squared 1/2. That'd be the case for all of them. And we have to sum them together. So this would be this one. Let's see what the electric field is for those two. That'd be the integral 2k q 1 equals a squared plus y squared 1/2, and y is changing. The a is staying the same, so dy, so that equals 2k q a squared plus y squared 1/2 2 divided by 2y. Y changes, so that equals 2 e6y. E6y equals, cancel this, and cancel these two. E6y equals k q a squared plus y squared, square root of that. And also need to do the same thing for the other ones. So if I did 2 to be r, seems like it should be the same thing. Oh, I see. It depends on the distance. So I integrated this. Here, sine of 0 is 0. Would be theta. I think it'll be the same. Just the angle would be different. But let's say the same y. The y was here. It would actually be r2 is a squared plus minus, I think. For this one, the distance would be y a minus y, or y minus a. The whole thing right there is a. I subtract y, and that's my value. So if it was here, we'll have a. Um, a subtract, so if it was on this part right here, would have a minus y, and that'll be the difference. So the integral here is from 0 to y, e 2 y equals kq a squared plus y squared to the 1/2. That's going to be the integral from, actually, let me do the whole thing. R instead would be e2 equals the kq 1 over, and this is a minus y, y minus a. That's y minus a. So it can work out. So if this is y minus a is a negative this, and it is negative. And if it's here, y minus that positive a gives this difference. Right? So it's 1 over, this is still a squared plus y minus a squared dy, that equals kq dy over a squared plus y squared minus 2ay a squared. So that equals kq integral dy over a squared 2a squared plus y squared minus 2ay. And y is going to still be from 0 to y. If that is y is 0, uh, a is negative a distance, and so forth. That works. So that equals kq ln 2a squared plus y squared minus 2ay divided by a squared, oh, divided by 2y minus 2a. So that equals kq ln 0 2a squared plus y squared 2ay divided by 2y minus a. And the last one, everything should be the same, except it should be y plus a. Here, y plus a. When I say here, I'm talking about this for these bottom two. We have y 0, or still y minus a. Oh, this were r. So I got to go from the actual one. This was r. Still a. Y plus a. This is y plus a, because y is y negative a. Give me a negative, let's say negative a over 2 plus a 1/2. Yeah, so it's y plus a. It should be the same, except that'll be a plus. E3 would equal kq ln 2a squared plus y squared plus 2ay over 2y. Means basically we have to add all of these together. 2 times this and 2 times this and 2 times the other one, and it should give us the field. But there's probably a simpler way to do this. Let's see what the solutions say. But that'll give me a lot of points. Zero. Got to do the cosine thing to get only the cosine part of it. This is like the general one. Crap. to do theta is y minus a over a. Like there it is using the equation 310. Not a big help. The only thing missing here is to make sure to remember to do the sine and the cosine, the sine for those two to get the y component only. Maybe I should be able to just multiply this by sine, the full one. So for number two, sine of theta is y minus a over a. So this would be times y minus a over a. And this would be times y plus a over a. So this gives me the y component filled. See some things cancel. Does it look similar to the other one? The thing is, the magnitude is the same, but they're opposite. That it should cancel out in the center when y equals 0. So the first one equals 0 at y equals 0. Equals 0 doesn't equal 0. Perhaps something is incorrect there as well. It's like the solutions, just remember the formula. this right, just calculate E and then put in sine theta, since I'm picking that to be theta. Like a good place to take a break. I'll be back either later or tomorrow to continue some more either electrodynamics or quantum. Uh, Drop a like, comment, maybe show up. Look for me in the future.